I was very lucky to be able to meet and work with our speaker today, Riya, who's a Master of Engineering Leadership candidate at UBC. She's an architect by training, originally from India. And so Riya and I have been working on this, well, I should say, Riya has been working on this and I learned from her. I have learned a lot from her, and she has been most graciously humoring me throughout this summer, all my never-ending questions and comments and demands and all that. I'm very glad that we have this opportunity to talk about some of the stuff that we have worked on and some of the things we have found, which we think have important implications for our collective efforts to our more energy efficient, lower carbon buildings and sustainable cities.
Thank you, Safir. I will just go ahead and share my screen. So hello and good afternoon, everyone. Thank you for the introduction, Safir. And thank you everyone for being here today. My name is Riya, and today we will be looking at the embodied and operational carbon emissions of single-family residences built according to the various tiers of the DC Energy Step Code. Safir introduced me pretty well, so I will just skip through this. But most importantly, thank UBC Sustainability Initiative for providing me with this opportunity, BC Hydro for financing the project, Safir Firoshini, my mentor for this project, City of Richmond, and moving on. The agenda for today's presentation is we will be first looking at the background and need of the study, quickly talk about the building selected as the base of the study and the methodology, do a comparative analysis of the various inputs, and finally talk about the results and the conclusion. A quick fact, buildings are the third highest GHG emitting sector in Canada. To talk about the background of the study, first let's take a look at what embodied and operational emissions are. So embodied emissions are the greenhouse gas emissions that occur throughout the life cycle of the building, which includes before, during, and after the construction of the building, operation and demolition. So they are associated with activities like extraction, manufacturing, transportation of construction material, as well as construction processes. These also account for any major renovations and end-of-life demolition. Operational emissions, on the other hand, are the greenhouse gas emissions released during the functioning of the building from energy-consuming activities like heating, cooling, ventilation, and lighting of the building. Embodied emissions are calculated in terms of global warming potential, which is expressed as mass equivalent of CO2 or carbon dioxide. Embodied emissions, along with various environmental impacts, are quantified by carrying out a whole building life cycle analysis through different life cycle stages, which include resource extraction, manufacturing, transportation, construction, operation, and demolition of the building. So life cycle analysis, it also gives us the results for other factors like eutrophication potential, ozone depletion, but for the purpose of this study, we will only be looking at the global warming potential of building materials, construction techniques, and building energy systems. So as we know that building sector accounts for almost 40% of the total greenhouse gas emissions, out of which 28% come from building operations and the remaining 11% are the embodied carbon emissions. And by 2050, it is projected that these embodied emissions are going to go up by 49% and operational emissions will reduce down to 51%. And a building is truly net zero only if both its embodied and operational emissions are zero. So this is precisely why we need to focus on the reduction of embodied carbon emissions while our buildings become more energy efficient. And the graph here shows that the overall carbon emissions can be reduced down to 80% if we build more efficiently. So this study examines the embodied emissions of building materials and mechanical systems that are broadly used to increase the operational energy efficiency and reduce the operational GHG emissions of buildings. The initial step to reduce embodied emissions is to identify carbon hotspots, that is, the materials or systems that contribute the most to a building's embodied emissions, And this is done by carrying out a sensitivity analysis and conducting a whole building life cycle assessment. To take a quick look at the BC Energy Step Code, it is a voluntary performance-based energy efficiency standard that provides an incremental approach to build higher energy efficient buildings that go beyond the requirements of the BC Building Code. And for Richmond, the current require for new single-family dwellings is compliance with Step 1 requirements, and the city plans to adopt Step 3 requirements for all single-family houses in 2020. These are the key performance metrics used to tabulate the performance of the building and the energy consumption of the building. The minimum or the threshold values have been listed in the step code, and in 2019, there were 2 revisions made to the step code. First, the TEDI values were updated based on the adjustments in the heating degree days. And secondly, an alternate option was also introduced to comply with the building envelope performance target by showing a percentage improvement of the annual space heating demand over the reference building. However, for this study, we chose to comply with the revised study targets as the percentage approach would have been too easy to comply with. So as we know, this energy step code is concerned with energy efficiency, but it does not necessarily guarantee deep reductions in the operational emissions of buildings, especially in the lower and intermediate steps. So this study was done by Integral Group, and the figure here shows that depending on the building type, depending on the type of building energy systems, even houses built to step 4 and 5 may have significant operational emissions. So thus, it is important to consider the trade-off between the embodied emissions of the energy conservation measures that are used to reduce the operational emissions and meet the criteria of energy step code. And the overall reduction in operational emissions can therefore be variable, and it definitely requires more attention. So to segue into the building information, based on the recent submissions to the city, a typical design was chosen as baseline of the study, which was representative of step 1 houses in Richmond. So what we have here is a 2-floor house with a total area of 346 square meters and a height of 9.8 meters. For the purpose of this study, we are considering the lifespan of the building to be 60 years, which is commonly used for conducting whole building LCAs. And in the figure here, we can see that the house has a typical east-west orientation with a garage and an entrance porch towards the west and a patio on the east. And the features or the parts highlighted in warmer colors have been included in the study. Moving on to the building plans, we can see here that the ground floor has a 2-car park garage, foyer, den, powder room and staircase nicely stacked up in one line, a double height living room here, dining and kitchen. And the important thing would be to note the fenestration, which is maximum on the east and west sides of the building. On the upper floor, we have 4 bedrooms. So the step 1 house has the following structural assemblies and insulation materials. The exterior walls are composed of 2 by 6 inches wood studs and have R20 batt insulation. The truss roof has R40 batt insulation. There's a 4-inch concrete slab with 2.5-inch EPS insulation. And there's R31 batt insulation in the floor. And the windows are double glazed, which have a U value of 1.77 and a solar heat gain coefficient of 0.4. So major and minor energy upgrades were made to the insulation of these assemblies to suit the requirements of energy step code metrics. Moving on to the methodology, we first carried out a literature study which included study of concepts like embodied and operational emissions, how whole building LCAs are carried out, types of insulation that are available in the market, and a thorough scan of similar studies that were conducted. This was followed by the building selection, which was explained in section 2, and then an assessment of scope, defining system boundaries, establishing the scenarios which were to be used in the study, and determining what all components would be included and excluded in the study. The most important step was identifying types of calculations and determining the methods and softwares to carry out these calculations. So we divided the calculations in 3 parts. Assessing embodied emissions for structure and insulation are calculated using whole building LCAs by the help of Athena Impact Estimator software. We primarily used assembly method for calculating the global warming potential for structure only, and then standard EBT values were used for assessing the values of insulation and combine the structure and insulation values together into a hybrid method, which I will talk about more in detail. For the embodied emissions of mechanical system, an existing thesis was used, which was written by Barbara Rodriguez. And in this thesis, she defines equations for global warming potential of equipment, distribution, and refrigeration. But for refrigeration, we used the City of Vancouver policy guidelines for green building rezoning. And lastly, to show the compliance with the energy step code, the operational emissions were calculated from HOT 2000, which is an energy modeling software typically used for single-family residences, and showing compliance with the step code. This was followed by modeling the 5 houses and carrying out analysis and providing final recommendations. So the tables here show the components that were included and excluded in the study. So we typically excluded all the site features, interior finishes, staircase details, and all the services except space heating, cooling, and hot water supply. And then all the furnishings were excluded as well from the study. So these are the 5 cases which were used in this study. The existing building design is used as a baseline case, and then minor energy upgrades were made to step 2 and 3 houses in terms of changing the insulation or decreasing the U value of the glazing. And then major upgrades were made to step 4 and 5 houses by changing the wall to window ratio, and then using insulation which have significantly higher R values. So these were the few challenges we faced while using Athena Impact Estimators in the sense that it had limited assembly and envelope options. Insulation values were available only in multiples of 10. So if we wanted to input insulation of R22, R24, there was some sort of assumption happening there. There was no option to add U value for windows. And most importantly, through various discussions from industry experts, we found out that the global warming potential values for insulation that go at the back-end calculation of Athena are hugely underestimated. So to offset this disadvantage and to get more appropriate results, we used a stripped-down model in Athena with no insulation to get the total global warming potential from structure only, and calculated the embodied emissions for insulation from industry EPDs and the table listed here. And the 2 calculations were then combined to get the total embodied emissions for structure and insulation. Moving on to the embodied emission calculation for mechanical system, it was again divided into 3 parts: global warming potential for equipment, distribution, and refrigerant. For equipment and distribution, we used an existing thesis by Barbara Rodriguez, and in her study, she defines the following equations, which are listed here, that list down material quantities of equipment, which is MEQ, distribution, that is DMQ, and the embodied carbon content, or ECC, from equipment and distribution. For MEQ and DMQ, the weight of the systems were the weight of the heating and cooling equipments, and piping and ducting were divided by the total heated floor area, and the ECC values were obtained from the tables which were provided in the thesis for standard building type and packaged rooftop heat pump system, which was the closest approximation that could be made. And then these were the final per square meter values for GVWP of equipment and distribution. For refrigerant, We use this equation, which is provided in section 6.1 of City of Vancouver Green Building Policy for Rezoning. And here A is the symbol for number of years. GBWPR is the global warming potential of the refrigerant. RC is the refrigerant charge in the system. L is the life of the system in years, which in this case is 15 years. A is the moderate floor area, that is the heated floor area. And then this equation assumes an annual leakage rate of 2% with 10% end of life leakage. All these values were calculated for total heated floor area, that is 204 square meters, and a lifespan of 60 years, which is the same as our LCA study. So let us now take a look at the different values obtained for each step code houses. This table here compares the energy upgrade made to each step code house to comply with the energy metrics. So as you can see, the roof insulation was changed from R40 loose filled to R60 blown cellulose in step 3, 4, and 5 houses. The wall insulation was increased to a combination of R28 batt insulation with 2 inches XPS. Similarly, the insulation in slab on grade was changed from 2.5 inches to 3 inches XPS. So I want to point out here that for the space heating, cooling, and domestic hot water, the step 1 to 4 houses use the following two options to compare the difference in operational emissions. Option 1 uses natural gas condensing heater plus a central split AC system for cooling, and then natural gas condensing boiler for domestic hot water. And option 2 has an air source heat pump for both space heating and cooling, and a natural gas condensing boiler for domestic hot water. The requirements for step code 5 houses were only possible through a fully electric sourced heat pump for heating, cooling, and domestic hot water. Similarly, the insulation options were modeled in Athena for different step code houses, and few approximations and assumptions had to be made based on the options available in Athena, which weren't the same as they were input in HOT 2000 software. And then these were the final values obtained from HOT 2000 for performance energy metrics. So just notice the increase in electricity consumption and decrease in natural gas consumption from step 1 to 5 houses, and we will discuss this more in the results. And then finally, let's take a look at the results. So to first compare the embodied emissions for structure and insulation from Athena Impact Estimator and the hybrid method, the values in yellow are the values obtained from Athena Impact Estimator software, and the green are the hybrid method. And as we can see, the difference in values is more for higher step code houses, especially step code 3, 4, and 5. Because these houses use significantly more amount of XPS insulation, which is a highly carbon intensive insulation. And based on these results, it can be concluded that Athena significantly undermines the global warming potential for insulation materials and may not be the best software choice to carry out highly precise analysis. So based on these results, the values obtained from the hybrid method were finally used for further analysis. And then to take a look at the total embodied and operational emissions, in the option using air source heat pump, the shades of blue represent embodied emissions from structure, insulation, and mechanical system. And the green values are the operational emissions in the option which uses air source heat pump as the primary source for heating and cooling. And then interestingly, the operational emissions for step 2, 3, and 4 houses are more or less the same. And this is because the space heating is virtually decarbonized as we're using electricity as primary fuel source. And by changing the space heating load, the total emissions from water heating does not really change. So there's a difference of 51 kilograms CO2 in the operational emissions of step 4 and step 5 house. And this is the figure that is essentially coming from the global warming potential of space water heating systems, which essentially remains the same in all step 4 houses. And again, the step code 5 house was fully electrified. Similarly, these are the total emissions for the option that uses natural gas boiler as the primary space heating. And then note that operational emissions changed significantly in all the step code houses. And step 5 is fully electrified, like I said, and the amount of XPS used is more in step code 3, 4, and 5 houses. So for this study, the use of XPS for meeting the step code requirements was intentional to show the change in embodied emissions of insulation. So as we know that XPS is a highly carbon intensive insulation, which is more commonly used, the compliance could have been made using any other insulation as well, but the jump would not have been drastic. So this is a comparative analysis of the previous two graphs. And then remember how we talked about the energy step code not guaranteeing the reduction in operational emissions. This is, we can see there's a significant difference in the operational emissions of houses using air source heat pump and natural gas boiler, which are, the difference is almost the double. So this goes on to show that the requirements of energy step code can be made through different energy systems, which will each have different operational emissions. Similarly, these are the results of total emissions on a normalized basis. And by normalized, I mean we divided the total values by the heated floor area. So the point of confusion here was whether to use the heated floor area or the total floor area, but to keep the basis of the comparison the same, we used the heated floor area, and these were the final figures that we got for embodied emissions and the operational emissions. Moving on, this figure shows the contribution of the structure, insulation materials, and mechanical systems to the embodied emissions at the two ends of the energy step code ladder, that is step 1 and step 5 house. Note that there's a significant increase in both the absolute and relative contribution of insulation materials to the embodied emissions when comparing the step 1 and step 5 houses. Next, we have the figure that shows the contribution from various components of the mechanical system of to the embodied emissions. So there's a very large contribution of the refrigerant, which accounts for almost at 84%. And in this case, we're using our 410A refrigerant, which is a commonly used refrigerant type. And the COV equation that we looked at earlier assumes an annual leakage rate of 2% with 10% end-of-life leakage. This figure shows the percentage component of the embodied emissions of structure of the baseline building design and different components that were used. So basically, these are the results we have obtained from Athena, and we've essentially left out beams and columns and floor because there were no changes made to these insulation, the insulation or the structural assemblies of these components. And we can see that there's a significant change in the embodied carbon of walls, and the change in foundation and roofs remains more or less the same. I mean, there's not much change. Finally, we have these chart here, which shows the comparative analysis of the contribution of each component towards the embodied carbon emission in step 1 and step 5 house. So we can see that the maximum contribution is from the foundation, which is about almost 43%, as foundation uses the maximum concrete. This is followed by walls, which is 40% in step 1 house and 43% in step 5 house. And all the other components, that is beams, columns, roofs, and floors, remain significantly less and constant. So to compare how the study, how our study compares with the previous existing studies, this was a study done by Urban Equation, titled Embodied Carbon White Paper, and what they essentially do here is carry out embodied emissions of multi-unit residential buildings, that is MORBs, and compare them with the Ontario Building Standard. And similar to Energy Step Code here, they have the Toronto Green Standard. And these are the results that compare for TGS Tier 1 to 4 and the reference buildings. And we can see here that the operation emissions reduced considerably from TGS Tier 1 to TGS Tier 4 houses, along with the embodied emissions. Secondly, this was a study done by Totland at the Norwegian University of Science and Technology. And what they essentially do here is keep the insulation same, but change the thickness of the insulation in all components. And as we can see that the embodied emissions change significantly from a thickness of 100 mm to a thickness of 500 mm. And moving on to the conclusion, we saw that the energy step code is not very effective in reducing the operational emissions of building, and it can have the unintended consequence of increasing the embodied emissions of building. Therefore, the relationship between the decrease in the operational emissions and the increase in embodied emissions should be more carefully studied. And as we know, a building is truly carbon neutral only when both its embodied and operational emissions have been eliminated. And as the operational emissions of a building are reduced, the contribution of embodied emissions becomes even more significant. And in a step 5 single family dwelling, for instance, the embodied emissions can account for up to 90% of the total emissions, which is significantly high. Due to the increased amounts of insulation used, the embodied emissions of a step 5 house can be significantly higher than the embodied emissions of a comparable step 1 house. And then this can be resolved by paying more attention to the environmental product declarations and looking at them in the conceptual phase of the design. And there should be more focus on the use of natural and low carbon insulation materials. To look at the mechanical systems, we saw that refrigerants are the primary source of embodied emissions of mechanical systems. And with the increasing popularity of heat pump, more attention needs to be paid to the embodied emissions of refrigerants. Lastly, it is important to collect data on the embodied emissions of buildings, and such data should inform policymaking at the municipal, provincial, and federal levels. Therefore, it is useful to report the embodied emissions and operational greenhouse gas emissions on both total and per unit floor area basis. So these are the few conclusions we had from our study. And with that, I would like to open the floor for any questions.